This will be a review on magnetism. Materials that can be magnetized are referred to as ferromagnetic materials. Not everything is ferromagnetic. Magnets always have two poles, a north and a south. Unlike poles will attract, while like poles repel each other. The magnetic field surrounding a magnet form what we call magnetic field lines. Magnetic strength is the strongest where the lines are closest together, which is at the poles of the magnets. Magnetic field lines always go out away from the north pole of the magnet and always enter in at the south pole of the magnet. Here's a demonstration of metal filings over a bar magnet. We can't tell where the field lines are entering or leaving, but we can definitely see the arched pathway between north and south and determine where the field strength is the greatest. Compasses are devices that respond to the Earth's magnetic field and other items that are magnetized, such as electromagnets and bar magnets. If you pass a compass around a bar magnet, it will change direction in accordance with the magnetic field lines. Here's a demonstration that shows several compasses surrounding one magnet. You can visualize how they follow along with the magnetic field lines. An electric current going through a wire generates a magnetic field. Passing a compass next to a wire that has current flowing through it, you can see that there is definitely an effect on the compass heading. A solenoid is a coil of wire. When electricity goes through a solenoid, then a magnetic field is produced. The more wraps of the wire there are on the solenoid, the more magnetic the electromagnet can become. The advantages of electromagnets are that they can be turned on, as seen here, or turned off, as it is here when it's disconnected and it's no longer magnetic. The automatic door openers in our school are examples of electromagnets. When the fire alarm trips, the power is cut off to those magnets and it releases the doors so that they shut for safety. Now let's review some of the math that went along with magnetism. Here are the equations that we used. The first two are for finding the magnetic force involved depending on what given information we have. The third one is for finding the magnetic field surrounding a wire, and it includes the constant mu naught, which is the permeability of free space, which is given as 4 pi times 10 to the negative 7 Tesla meter per amp. We also need the charge of electrons and protons, which is 1.6 times 10 to the negative 19 coulombs, positive for protons, negative for electrons. This information is given. Let's review some sample problems. This has a magnetic field of 16 teslas acts in a direction due west. A proton, and it reminds us the charge of a proton, is traveling due south at 8.1 times 10 to the 5 meters per second. What is the magnitude of the force acting on the proton? By listing all the given information, including the charge, and recognizing that the directions given, west and south, are perpendicular to one another, we know that the sine of 90 degrees will be 1 in this equation. So we choose the equation F equals QVB sine theta. Then we substitute into that equation to solve for the force. So according to this equation, we will be multiplying all these values together. As far as the units go, because the Tesla is a derived unit, everything will cancel. Coulombs cancels coulombs, meters cancels meters, seconds cancels seconds, and the only thing remaining will be newtons, which is the appropriate unit for force. In the second example, it says a 2-meter long wire carries a 15 amp current perpendicularly through a 6 Tesla magnetic field. What is the magnitude of the force on the wire? Now, when listing out the given information, we find that we're given the length, the amperage, the magnetic field, and we're told that it's perpendicular, meaning an angle of 90 degrees. So again, we will substitute into the equation for force, this time using F equals ILB sine theta. Again, resulting in us multiplying all these values together and taking into consideration that the Tesla is a derived unit, which can be expressed as a Newton per amp meter, such that amp and amp cancel, meter and meter cancel. The remaining unit is Newton, which is the appropriate unit for force. In this sample, it says a 2 Tesla magnetic field is parallel to a 10 amp current traveling 5 times 10 to the 11 meters per second. What is the magnetic force? Well, the key word here is that it is parallel. Parallel will be 180 degrees. The sine of 180 degrees is 0. Therefore, no matter which equation we go with, when we multiply it by 0, the final answer is 0. So the real answer here is that there is no force. And our last example says electrons, again giving us the charge, traveling at right angles to a magnetic field experiences a forward force, or out of the page, of 7.3 times 10 to the negative 13 newtons when they are in a magnetic field of 9.2 times 10 to the negative 1 Tesla directed north. How fast are the electrons moving? So now we need to solve for velocity. We'll have to take the equation F equals qvb sine theta and rearrange to solve for v. Since in these equations everything is multiplied, it's simply a matter of taking everything that's on the side with v and dividing it to the other side, placing it under force. Then when we substitute in the values, we will have a force in newtons divided by coulombs, Tesla, and everything will cancel except for meters per second, and we'll have our answer for velocity. Now, if we'd like to practice the right-hand rule with this problem, we take note of the fact that the force is out of the page, and the magnetic field B is directed north. And we would try to find out the direction of I. We'll use our fingers for magnetic field and our thumb for I and the palm of the hand for force. You can see, according to the right-hand rule, that if the force is coming out of the paper and the magnetic field is pointed up, that the current is going to be to the left, or you might say to the west. If you want to try right-hand rule on this sample, it says that the magnetic field B is west, and the velocity of the current is south. So a diagram of this would look like this, and since it's a proton, we'll use our right hand, point our fingers to the left, our thumb down, and the palm then would be facing away or into the page. And there are some sample problems. Good luck on studying for your test.